actually quite a deeply technical talk. At least you won't be falling asleep. If this was post-lunchtime, it might be a different matter. Yeah, my name's Guy Davidson. And this clicker, there we are. Go. There we are. So I'm the former head of engineering practice at Creative Assembly. I'm currently the head of engineering at a company called 6 Impossible Things Before Breakfast. We're making a game engine. It'll be great. Do look out for it when we announce. I'm the chair of programming languages for the British Standards Institute, and I'm also an ISO C++ global expert, which is a lot more exciting and flash than it really is, than it sounds. I'm a committee member of the C++ Standards Committee. They're the people who make the language that I'm sure many of you use. How many C++ programmers in here? That's a relief. Thank you. Good, good, good. I'm also the chair of the ACCU conference. You can find us at accu.org. If you've ever thought of doing a talk, please consider submitting. Our call for papers is open. Go to accu.org. I'm the game dev track chair at CPPCon. We had our first game dev track. It was quite successful. So again, if you fancy speaking, if you fancy traveling the world on somebody else's wallet, this is the way in. I'm a regular speaker in Europe. I've given this talk in Munich, Amsterdam. Anyway, Europe. I like Europe, despite being British. I play the piano. I sing first bass for the Brighton Festival Chorus. I run a film club. I grow my community. I do all sorts of things. I don't like to let the grass grow under my feet. Indeed, I wrote a book during lockdown with Kate Gregory. Anyone bought the book? Anyone read the book? You sweetie, thank you. Let the record show that about 2/3 of the audience have bought and read the book. Who was at my last talk? Right, I'll try and repeat fewer of the jokes then. Thank you. You can buy it. This is a slide that I didn't have. And I can wait while you do this. There's a nice discount there that'll make it nice and cheap. People taking photos of the... Oh, thank you. It works, you see. Marketing. It's a real thing. Here's our agenda. Please do stop me to speak up, slow down, and take notes. Tell me where I can improve the talk, because this is not the last time I'll be giving this talk. We're going to talk about non-integral values, standardizing non-integral arithmetic, standardizing C++ for non-integral values, and improving reproducibility of non-integral values. Right, let's start with our arithmetic operators. You know these, plus addition, subtraction, multiplication, and division. Each of the inverse functions, subtract and divide, can create results outside of the original domain. For example, addition on natural numbers stays in natural numbers, while subtraction can take us into the integers. Multiplication keeps you in the integers. Division takes you into the rational numbers. And rational numbers are ratios. The clue is in the name. The set of rational numbers is countably infinite. And interestingly, half of the rational numbers lie between negative and positive 1. You can express all the others as vulgar fractions, where the denominator is less than the numerator, or as the sum of an integer and a rational number between positive and negative 1. There's something beautifully analog about rational numbers. For every pair of rational numbers, there is another rational number between. Rational numbers are also quite reducible, thanks to the fundamental theorem of arithmetic, by cancelling common prime factors in the numerator and denominator. And if you search for rational numbers in geometry, you'll see yet more beauty. Has anyone used a slide rule? You should all learn to use a slide rule just for fun. It's quite intriguing, it's quite interesting. I'm rather fond of them, to be honest. There is something of the cosmos about them. Until you want to add them, then it becomes, well, I'm rather less enamored, because multiplying and dividing is pretty easy since you're multiplying integers, but addition is a lot tougher. You've got to do all this cross multiplication, and implementing this on a computer is quite a headache. You know, starting with modest values, it only takes a few additions to actually overflow your integer types, and you can keep a lid on things by trying to factorize, but more often than not, you won't be able to factorize. And you can't guarantee how long it will take for things to overflow. You could use an arbitrary sized integer class. Memory's cheap, but then it takes a long time, and you know, memory as well. And most of your clients aren't going to be happy when they ask you, how long will this take? And you simply say, well, that depends, because we like bounded operations. But we came up with a solution quite a while ago. It depends on who you ask when, because decimal fractions have been in use for several thousand years. But common representation is a different matter. John Napier, in his book on constructing tables of logarithms, which was published at the beginning of the 17th century, introduced the decimal point. And that tells us that we're now approximating via sums of powers. So the first digit after the decimal point gives us the number of tenths, the next number of hundredths, and so on. And by adding more and more negative powers of 10, precision can be improved, but there are only a small set of numbers which can be represented exactly, because since we're in base 10, whose prime factors are 2 and 5, the only rational numbers that can be represented exactly are those whose denominator is representable as a product of powers of 2 and 5. So for example, 1/8 is 0.125 or 125 thousandths. 3/40ths is 0.075 or 75 thousandths. And other numbers aren't so lucky. In fact, most numbers aren't so lucky. Here's 1/7. This is represented as 0.142857 recurring. However, I got this when I asked Clang to output the result. And as you can see, it's quite wrong. All numbers that are not exactly representable will recur. The inexactitude might seem to spell doom for engineering, but empirically it doesn't. Here we are in a building. It's not falling down. So we got it right. Who knows what the size of the observable universe is? You, guess. Guess, go on. 5. No, that's the wrong answer. The actual size is 8.8 times 10 to the power 26 meters, which is large. But that exponent, 26 decimal places, gets you the width of the universe to the nearest meter. 38 decimal places gets you the width of the universe to the nearest atom. And they're quite small. So honestly, 26 decimal places is more than enough. There we are, 8.8 times 10 to the power 26. Magical number. What's this value? Now, you might tell me it's 26,998 because we're all very good at going from hex to decimal just in our heads, just like that. But you'd be completely wrong, because if you assume this is an integer, then yes, it is that value. But what I haven't told you is that the lowest 4 bits are reserved for negative powers of 2, and this value is actually 1,687.375. And adding and subtracting these numbers is simple enough. We don't care about powers in those operations. But multiplication is a bit of a different matter. If you pass these bit patterns to the multiplier, you get 288, which is clearly wrong. As you can see, this is not 16. To get the expected value, you have to right shift by 4 bits. And this tells you straight away that there is some overhead for working in fixed point arithmetic, because it isn't natively supported by C++, so you have to manually write a fixed point class. And you might decide to use CPU intrinsics. Some processors do implement fixed point out of the box. But that final part of the operation where you shift by the number of bits in the fractional part also highlights another problem. Precision falls away with each calculation. Simulations typically make heavy use of Newton's laws of motion, which involves a lot of multiplication. And it won't take long for your model to diverge noticeably from user expectation through this lack of precision. The problem we have is that the binary point is fixed at bit 4, hence fixed point, you see. If we want more precision, we would have to divide by even greater numbers. That would yield an even greater error. In the prior example, it was simply, if we simply left the value alone and shifted the binary point to the left after each multiplication, there would be no loss of error, but we would soon run out of magnitude. So let's look at another representation of numbers. Now in the first line, we're performing addition. 3 decimal places in each number are used, but the second number has a higher magnitude. Oh no, we're going this way, aren't we? Hello. There you are. That has magnitude 10 to the power 1. This is a magnitude of 10 to the power 2. The result of the addition has 4 decimal places, and the result of the multiplication has 5 decimal places. So this looks good. We can accommodate the expansion of precision rather more easily with fixed point arithmetic. And rather than keep the decimal point in the same place in the number, we're storing the number in two parts, a value and a magnitude. The value part is known as the mantissa, while the magnitude part is known as the exponent. I learnt recently that it's not called the mantissa, it's called the significand. We stopped using the word mantissa in the 80s, but everyone still calls it mantissa because everyone reads old maths textbooks. Let's try something in binary. So we have to make some decisions. Which part is the exponent and which part is the mantissa? Well, I'm going to choose the bottom 6 bits for the exponent and the top 10 bits for the mantissa. And that gives us this. So let's unpack this. When we were in base 10, our mantissas lay between 0 and 10. For this example, I've decided that our mantissa lays between 0 and 1. And looking at the leftmost 10 bits, counting left to right, we have 1/4 plus 1/64 plus 1/512 plus 1024th. While the rightmost 6 bits total 11. And this gives us an exponent of 2 to the 11th power, which is, of course, 2048. So all of this evaluates to 550, and a similar approach to the second value evaluates to 0.2890625. But we've got a problem, because looking at the representations, we have this, and multiplying those two representations using standard integer arithmetic, which worked with fixed point arithmetic, it won't work with floating point arithmetic. And the process of floating point multiplication is actually quite a task. And additionally, the schema I proposed does not invite a unique representation for each number. So for example, the value on the right has multiplied the mantissa by 4, shifted 2 to the left. So the exponents have been reduced by 2, since 2 squared is 4. And also, how do you represent negative numbers or negative powers? Because that would cost a single bit of resolution for the exponent and mantissa. And another problem, the bigger problem that we're going to talk about, is interoperability. How do you communicate to your clients how wide the exponent and mantissa is? What if we're exporting a library to some anonymous third party? Well, there's plenty of room for error, and this sounds like a job for standardization. IEEE 754 is what you're looking for. Anyone heard of this? Good, a few of you. It's a very, very valuable piece of standardization. It was first published in 1985 and has undergone some revisions since then. In fact, the C++ standard refers normatively to document ISO/IEC/IEEE 60559:2020. You see, this just rolls off the tongue for me. You get used to it. But the world of standardization is full of all of this, really. But this is ISO importing third-party standards into its ecosystem. And it's the same thing as the latest revision of IEEE 754. You don't need to read this standard. You can simply rely on your vendor implementation to be conformant. This is my straight face. Anyone play Rome Total War? Bless you all. It was released on the 10th anniversary of the first broadcast of the US sitcom Friends, by coincidence. And it featured multiplayer action over the internet. And this was quite hard to achieve because there were many megabytes of state which had to be synchronized with each player at 10 hertz. And even now, that's quite a big ask of the internet. But back in 2004, it was lunacy. Even transmitting the delta from tick to tick was infeasible. And the only thing we could do was transmit the commands that were issued to the simulation of the worlds to each agent and update each agent's simulation equivalently. And this was a surprisingly tricky problem because it's easy to write code that's not deterministic. You might forget to fully initialize an object, or and so you get state data from the stack instead. And you might pass a reference to an object to the camera and inadvertently change things locally, and there were a large number of things that would cause the simulation to diverge. It was an awful problem. But we devised programming guidelines and debugging strategies, and we locked it all down so that it was deterministic. It was completely deterministic. And Sega are very keen, obviously, to see a console version so that Xbox and PlayStation and even Switch can join the fun with PC players. And it would be quite feasible to have Switch players competing against one another, or Xbox players competing against one another. But no publisher wants a fragmented audience. You should be able to connect to a lobby and play with anyone at all. And part of you might be thinking, well, crossplay is a thing. You know, why would this be so hard? And to be clear, when you see crossplay, aside from the fact that it's not very well defined, you know, you aren't chucking a lot of state around the internet and hoping for the best. You aren't running detailed simulations of 100,000 entities with impact-specific animations. And you might go to think, well, why won't the same code work the same way and yield the same results on different platforms, because 2 plus 2 is always 4, isn't it? Or is it? Well, actually it is. But you get my drift. You're all engineers here, aren't you? Most of you are engineers, I'm guessing. And you know about the butterfly effect. So I've got a simple example here, 42 lines of code that explain what's going wrong. Come on. No. That's interesting. It's more like it's... Just one moment, everyone. No, I want this window. This has proven to be the trickiest part of this presentation. Right, can you all read that? No, you can't. Okay, it's a bit small. But look, the point being, we've got some code up here, and we're compiling it on 2 compilers. Are you all familiar with Compiler Explorer? Yeah. Matt Godbolt, God amongst men, really. We've got 2 compilers here, the NVIDIA compiler and the Clang compiler, running the same piece of code, and things go wrong immediately about here. And what's happening is, why is this disappearing off the bottom? Yeah, what's happening here is we've actually got different output. And that's a real problem. That's a real problem. Things start to go wrong at the very first calculation. Direction X and direction Y are unaffected by the difference in distance. Proj vector X is also unaffected. Proj vector Y, though, is divergent. So I want to focus on reproducibility across implementations. Right, this is going to be quite annoying. And I can't even see the thing to... Oh, my... There we are. Let's have that. Sorry about that. Right, standardizing non-integral arithmetic. But thank heavens, the IEEE decided to standardize floating point arithmetic. Back in 1985, the International Electrotechnical Committee, they thought, we'll have that, and they published it in 1989. And then the BSI, the British Standards Institute, adopted it in 1990. IEEE revised it in 2008. Broader standardization bodies were pleased with this work and republished the first revision as that. IEEE published a second revision in 2019, which ISO-IEC republished in 2020. And I'm going to rush you through this, but I strongly recommend that you find a copy for yourself and devote a weekend to reading it. It's about 80 pages. It took me about 4 hours. Might take you a bit longer, but not that much longer. It's, 2 glasses of wine, really. So I'm going to stay current and focus on the latest version. So the standard specifies formats for binary and decimal floating point data. Addition, subtraction, all of that. Conversions, more conversions, more conversions, and some exception handling. So I'm going to do some foreshadowing here. Fuse, multiply, add. That's problematic. I'm also going to highlight parts that aren't especially relevant to portability. There we are. Now, in the section on definitions, abbreviations, and acronyms, there is some more foreshadowing. So, language defined. That means behavior defined by a programming language standard supporting this standard. And that comes up a lot in standardization. You have bits that you can't fully specify because hardware might not allow you to. But if everything conforms to the language, everything's fine. Unfortunately, we also have this concept, implementation defined. So that's behavior defined by a specific implementation of a specific programming environment conforming to this standard. So straight away we can see that this standard allows divergence. Onto the meat of the standard. So binary formats, you might be familiar with these if you're into floating point. There's the 64-bit. And the choice of which of this standard's formats to support is language defined, or if the relevant language standard is silent or defers to the implementation, implementation defined. The names used for formats in the standard are not necessarily those used in programming environments. So they're called binary 32 and binary 64. You might know them as float and double. The standard then goes on to tell us what I said earlier. Floating point arithmetic can only represent a finite subset of the continuum of real numbers. Consequently, certain properties of real arithmetic, such as associativity of addition, do not always hold for floating point arithmetic, so order of evaluation matters. So that's clause 3. Clause 4 deals with attributes and rounding. So attributes are associated with a program block. They use different language here. This is a specification for all languages. A program block is just some region of code. It could be a function, it could be a source file. There are two kinds of attributes. Some change the operation of functions, and some are implicit parameters. Rounding falls into this category. There are 5 rounding modes. Rounding is a beast. During the production of Rome Total War, as we were trying to achieve determinism, we would find desynchronization would occur on machines with different graphics cards. So this is the same tool chain, same processor, different graphics cards. And it turned out that one graphics card driver performed a different rounding mode, or preferred a different rounding mode, and changed it while executing the driver code and did not change it back. This made me quite grumpy. Clause 5 is where things get meaty. Nearly a quarter of the document is taken up with this clause. The standard is quite comprehensive, identifying the set of functions that shall be added by a conforming implementation. Particularly, we have rounding functions, next and previous functions, log functions, or arithmetic operators. Obviously, these, the usual arithmetic, but also square root and fused multiply add. And this is where things become problematic, because FMA computes x times y plus z, and it rounds only once to the destination format. Now, if you do a multiplication and then an addition, this would give you 2 rounding operations. And that's where it kind of falls apart. And this was the problem in the example I showed you, was that one compiler was using FMA and another compiler wasn't. Now, we've witnessed at 6 Impossible Things, we've witnessed all sorts of divergence with different optimizations. And it's sadly not a sufficient solution to merely, break down all the expressions and separate them and things like that. I mean, it's a start, but it's just not enough. There's a truckload of stuff going on here as well. There are conversion operations, sign querying, negation, different types of rounding, ordering, comparison. One day I'll do a full walkthrough of the standard. It'll take me a day, and it'll be a great piece of video for the internet that everyone can brag that they've watched. But is anyone familiar with the Goldberg paper on what every software engineer should know about floating point arithmetic? Okay, there's a link on my final slide to it, but write down Goldberg. Let's rush on for today. Infinity is a remarkably simple concept as far as the standard is concerned. Do anything with infinity, you get infinity. And it's also signed. Nans, on the other hand, are really quite subtle. You use them for uninitialized objects, loudly signaling invalid operations, such as finding the square root of a negative number. Anything that's gone wrong, use a nan, and they propagate. Once you have a nan in your calculations, nothing works. Everything's wrong. The sign bit might seem trivial, but there are some interesting edge cases. How do you choose the sign of 0? So on to clause 7. This talks about exceptions. And this can be caused by invalid operations, as I mentioned. And there are some things that you can't do with infinity. You can't multiply 0 by infinity. You can't divide infinity by infinity. Division by 0 gets its own exception. So does overflow, where a result can't be represented in the target's type. And underflow happens when a result is smaller in magnitude than can be represented. Inexact happens if no other exception is raised and the result differs from what would have been computed were both exponent range and precision unbounded. And this is a matter of magnitude. Clause 8 also talks about exceptions. Clause 9 describes some extra nice to have operations like trig functions. So we have 2 more clauses to go. Clause 10 is where things get interesting. Now in clause 5 we looked at how to perform a single operation, and clause 10 opens with a summary of clause 5. Clause 5 of this standard specifies the result of a single arithmetic operation. What happens when you add 2 numbers? You pretend you've got infinite precision available and then round to the destination format. Every operation has an explicit or implicit destination, and for numerical results, one rounding occurs to fit the exact result into a destination format. That result is reproducible in that the same operation applied to the same operands under the same attributes produces the same result on all conforming implementations in all languages. And that is a bold statement, all conforming implementations in all languages. Now, language standards define syntax for expressions that combine multiple operations. So as we saw, A times B plus C times D. A rule for expression evaluation encompasses the order of evaluation, the formats of the intermediate results, and when assignments to explicit destinations round once and when twice. And this is all a little exciting to me because the implication seems to be that if you write your code using single operations rather than expressions and write your own maths library, you're golden. And I'm not saying that's trivial, but it's not impossible. Now, the final clause was added to the first revision of the standard in 2008, and it's entitled Reproducible Floating Point Results. And this is the shortest clause in the standard, coming in at about a page and a half. I could read it out in its entirety, we're short on time. But it describes what the reproducible operations are, which is basically all the ones that do something to inputs legally. It describes a reproducible status flag and a reproducible format, but significantly it defines a reproducible attribute, which is an attribute that is required by our language standard in all implementations. If you remember, an attribute is like, saying, hey, this block of code, everything's reproducible. The clause goes on to say, any conforming language standard supporting reproducible programming shall support the reproducible results attribute, support a reproducible format, and provide means to explicitly or implicitly specify any sequence of reproducible operations on reproducible formats supported by that language. And it shall also explicitly define a whole bunch of things, including reproducible results attribute, which indicates when reproducible results are required and when they are not. And the final part of the normative standard instructs users how to obtain the same floating point numerical and reproducible status flag results on all platforms supporting such a language standard. And it's a list of programming guidelines, 5 do's and 9 don'ts. So this might come as a bit of a surprise because, typically implementations are 60559 compliant, aren't they? Which means that specifying the reproducible attribute in code should be all we need to get what we want: portable, reproducible, floating point operations. And why has nobody told me about this? Well, let's see how the standard does specify floating point behavior. Standardizing C++ for non-integral values. You might find this a slightly sarcastic section title, frankly. Is anyone here has anyone here, glanced or read the standard or taken a look at it? That's good. No, that's good. You're not meant to. You're not meant to, because most people will run away screaming. It's not a document for teaching C++. It's not even a document for explaining why things as they are. It just very precisely and unambiguously explains what they are. Right. Let's go back to the browser and start with basic fundamental, paragraphs 12 and 13. Just one moment, everyone. Come on. There we are. Right, don't need that anymore. Right, basic fundamental. We can't read that at all, can we? Okay, I'll read this out. The 3 distinct types, float, double, and long double, represent floating point numbers. The type double provides at least as much precision as float, and the type long double provides at least as much precision as double. They're all subsets, that's what it's saying. An implementation may also provide additional types that represent floating point values and define them, so we're not limited to those 3 types. And except as specified, and this is the important bit, except as specified in basic extended FP, the object and value representations and accuracy of operations of floating point types are implementation defined. That is to say, they are not 60559 compliant. And I don't know about you, but I felt a sickly panic when I read the object and value representations and accuracy of operations of floating point types are implementation defined. Strange things make me queasy. And I went scurrying to basic extended FP to see what was on offer. So I thought, okay, let's take a look at this. I'm terribly sorry about all of this. Right, so this is basic extended FP. Incidentally, if you probably can't read that. If you go to eel.is /C++draft/intro, you can get the entire C++ standard draft online. It's a very useful facility if you want to solve arguments with your colleagues. If the implementation supports an extended floating point type, whose properties are specified by 60559, floating point interchange format binary 16, then we have the type def name stdfloat16_t, and it names such a type. And it's defined, we get the floating point literal suffixes, that's fine. And the rest of those clauses say that. Unfortunately, that's not enough, because all it's saying is these things exist. And it says they're represented like this. Again, it says nothing about operations or accuracy or anything like that at all. Right, let's get this back. So it's not really much help, is it? But C++ basically has nothing to say about floating point arithmetic. It's really quite casual, and the reason for this is that not every implementation platform is IEEE 754 compliant. If the standard started mandating compliance, then things like microcontroller units would no longer be able to have standard implementations of C++. What do we do? Okay, so this is a less sarcastic heading, because C is also designed for platforms without IEEE 754 compliance. There is nothing mandating floating point behavior, but there are some annexes to the C standard which help us out. And more than half of the reference to the ISO IEC 60559 in the C standard are in the annexes in the index. We'll take a quick look. There are only 7 clauses in 9899, which is the C standard, including 1 clause on language and 1 clause on library, whereas in C++ there are 33. ISO drafting regulations have nothing to say about clause length. Anyway, Annex F spins us through 60559, much cited earlier. There's a macro called that, and if an implementation defines this with the value 202311, that means the implementation conforms to the specifications in this annex for binary floating point arithmetic. And there's a corresponding macro for floating point arithmetic, for decimal floating point arithmetic, which is interesting. Annex F goes on to cover a lot of 60559, particularly provides mappings for names. So for example, binary 32 becomes float, binary 128 becomes long double. Sometimes symbols are used. Compare signaling, not greater. That's simply x is greater than y. Sometimes cases are changed. Next up becomes next up. So Annex F is great. It works its way through 60559, makes changes to names, introduces symbols, adds identifiers. You can't just say apply everything to ISO IEC 60559, apply everything in the standard. You have to actually spell it out and modify according to the prevailing standard and actually the drafting rules as well. Annex F9 covers optimization. This section identifies code transformations that might subvert IEC 60559 specified behavior and others that do not. There are statements about code removal, code motion, all of the kind of things you get with optimization, expression transformations, such as 1 times x equals x. Trivial operations like comparing x to x. Dealing with constant arithmetic at compile time, but the wording is quite careful not to provide a way for compilers to play fast and loose with the standard. And we'll come back to optimization in a moment. But the rest of the annex looks at math.h, lgmath, tgmath.h, naming the functions I'm sure you're all familiar with. Now, Annex G looks at complex arithmetic. Annex H looks at interchange and extended types beyond float double and long double. But what about ISO IEC 60559 clause 11, reproducible floating point results? Where is that? It's not mentioned. It's just not there. Maybe it's too hard. Let's look at optimization. As far as I can see, fusion of instructions, so that's x times y plus z into FMA, and reordering are the 2 methods of optimization available to the compiler. We've already seen how FMA can be problematic, and as I'm sure you've worked out by now, reordering is not an option for reproducibility. Reordering takes place according to the characteristics of the processor being targeted, so reordering may differ between targets. So how do we overcome reordering and fusion? Well, we could try rewriting the code, putting semicolons in between things. The compiler cannot reorder those, and so we have consistent operation. But this is just the instructions being passed to the instruction pipeline. I don't know if these platforms will reorder instructions on the fly. I'd expect that 754 compliance would prevent that, but I've yet to test this thoroughly. Let's look at how two compilers enable optimization. First MSVC and the negative FP option. FP fast, that's the obvious choice for optimization. It's nice and simple. This does everything. It allows the compiler to reorder, combine, or simplify floating point operations. All sorts, really. FP precise is default compiler behavior, and the compiler preserves all of the source expression ordering and rounding. The compiler doesn't perform transformations, basically. But the difference in performance can be quite staggering. I've seen a 3-fold increase in running times when testing our code using FP precise over FP fast. What about GCC? Float store, don't store floating point variables in registers and inhibit other options that might change whether a floating point value is taken from a register or memory. No math error, unsafe math optimizations. Who would use that, really? No trapping math. And they also have a fast math, which combines all of these together. And if we turn off all maths optimizations while write single operations for expression, and write our own maths library, are we golden? Maybe. I'm currently in communication with some core experts about this. Core is the part of the C++ standard group that relies on, that writes how the language works. The other group is called library. They write how the library works. Look for an updated version of this talk. But one of the reasons I like using C++ is operator overloading. The ability to build complex expressions that look like they've come out of a textbook, and they are easy to understand, and they do what they're supposed to do. And when I started programming in assembly language in the 1980s, I had an awful time putting maths functions together. Have I really got to do things one step at a time? There has to be a better way, so I have some ideas. I'd like to thank the organisers for bringing me a cup of boiling water, because I have my own tea bags, so I have tea up here, because I'm British. Right, improving reproducibility of non-integral values. Here's the actual business. So the first crack of the problem is a class called deterministic game float. So we have a geometry template library, which takes an arithmetic type as a parameter. And currently we're defaulting to float. It's working fine, but it's not deterministic. So what we need is a type that can be taken as a template parameter, exhibits floating point-like properties, is reasonably precise, as fast as possible. We're making good progress. We expect to open source our library in the fullness of time, but can we do better? What about actually changing the standard? So introducing the class from the prior slide isn't going to fly. It's extraordinarily specific insofar as it actually sets aside 60559. What we need is some way of preventing reordering. So one idea that's been floated internally to my employers is the idea of having fences around which instructions can't be reordered, and these are rather like memory barriers. The ergonomics of this seems rather poor. They've been needed throughout all your code, and it would greatly reduce the legibility of your source. An idea I recently had was a new attribute, reproducible, which would identify a function as being immune from floating point optimization, and this would also advertise to the linker that link time optimization was not available for this function. Better still, a function qualifier, like const. Of course, one problem with such a function is that it must not call any functions which might affect its reproducibility. So this is quite a complicated bit of analysis that needs to be performed at compile time. It is horrifically hard. The same problem arises with the idea of pure functions, as proposed by Carl Etienne Perron in September 2015 in paper P0078. You can look at any of these papers. If you go to wg21.link and then add the paper number after that, in fact, just go to wg21.link and read the instructions if you want to keep abreast of what's happening in the standard. But this paper was discussed. It's been dropped by the author. But if you've been paying close attention to the standardization of C, which I'm sure you all have avidly, you'll know about paper N2956 on sequenced functions, which introduces pure functions to C. And it also snags the word reproducible. So we need something else. I've got a paper, P3375. It's pretty simple, and I define this enumeration and this class. And the class defines operators, but it specifies that execution behavior of operations on objects of type strict float shall preserve the literal meaning of the source code. Operations shall not be reordered or fused. And I imagine that this wording will need a lot of work, but it's a statement of intent. And there's another paper in the same sort of space. Oh, hang on. And this proposes rather dramatically deprecating FE set round and FE get round. Who uses these two functions? So they're safe for deprecation. And the idea is we replace them with a struct to represent the rounding mode. And there are typical floating point operations, add, sub, mul, div, FMA, square. And they're defined as binary functions rather than as operators. And they're all carried out with the rounding mode passed to the constructor of this type. And neither of these papers are near complete. So things might not look great for C++ 26, but there's always C++ 29. And incidentally, C++ 23 was published this week. It's taken a long time. So this is where we are at the moment. I showed you how humans and digital machines deal with non-integral values. Then we looked at how this has been standardized, how we incorporated that into our standard. And finally, I wondered how we can improve on this, taking us towards cross-platform floating point determinism. Thank you.